So we discussed Kc calculations. Now these Kc calculations, remember we said if a system reaches equilibrium, right, this is a point or a state whereby the reactants, since it's in their nature to be used up, but they are no more decreasing in concentration, while the products are no more increasing in concentration. So if we have A reacting with B to form C plus D, we said that equilibrium is when the concentration is no more decreasing, and the reason being that for chemical equilibrium we have forward and reverse reactions. So the reverse reaction is forming back the reactants, so that's why their concentration stops to decrease. So at that stage there, we said we can calculate the equilibrium constant by saying that the concentration of the product over the concentration of the reactants. Now recall that we said only gases, which you would see with the symbol G, and aqueous solutions, only gases and aqueous solutions, which you see with AQ, right, are used in the formula, are imputed, or rather are substituted into the formula. Then remember we said in terms of liquids and gas, in terms of liquids and solids, when we substitute these, right, we simply put them as 1. Okay, that's something we discussed previously. Now we did also mention that the value of Kc does tell us some stuff. If your value of Kc is bigger than 1, usually it's much bigger than 1, hence we use 2 arrows. This means that at equilibrium the concentration, it means at equilibrium the concentration of products is going to be greater than the concentration of reactants. Okay, and remember we said that this means that the reaction proceeded well. We say the reaction proceeded well. Okay. Because at the end of the day we want to form the products. But if our Kc value is less than 1, usually, e.g., maybe it is 0.6, 0.7, it means the reaction did not proceed well. Reaction did not proceed well because the concentration of the reactants is gonna be more than the concentration of the product. Okay, so that is it. And then now we looked at a method that we use to calculate Kc. Now in terms of the method of calculation, we said we use the Rice table. Now how do we use this Rice table? Remember we said R would stand for the ratio, I would stand for initial concentration, or you can also say initial moles. If you want to work in moles, you can say initial moles. Okay, and then C is gonna be change, right? Change. And then E is gonna be equilibrium concentration. Okay, and one thing we also should then take note of is that the units, if you are using concentration, the units here will be moles per decimeter cubed, right? So, and then lastly, we also then said that I plus C give me E. Ne, I plus C give me E, meaning the initial plus the change give you the equilibrium concentration. Right. Now, I hope this is okay, and we remember that. Just if you would like still a basic explanation than this, then you can just check out our previous recording. So right now we're gonna look at some questions regarding this and see how we can do them. So let's look at this question, right? It says to us that we have a hypothetical reaction that is taking place between A2 and B in a closed container, which means this is A2 here, it's a gas. 2B is also B is also a gas, and then AB is a gas. So they didn't want to give us, the normal things, like reactions like carbon maybe plus oxygen. They are choosing to work with letters, and we know that this is an exothermic reaction. I think this thing about exothermic and stuff, they will be quite important when you talk about Le Chatelier. For now, we're just dealing with purely the calculations. So X mole of gas A2 and 2 mole of gas B are sealed in the container. You are given the volume of the container. After a few minutes, equilibrium is reached. The contents of the container, they turn light red, because a lot is going on. These are forming that dark red, and then this dark red is forming colorless. So now you end up with just a light red in the container there. So at equilibrium, it is found that this is what you have of AB, and the value of Kc is that. Determine X, the quantity in mole of gas 2 A2 that was originally sealed in the container. So, good people, if your question you are given in moles like this, you are more than welcome to work in moles, so that but if you're working in moles, you must work in moles throughout. If you work in concentrations, you must work with concentrations throughout. Okay, so here I'm gonna say use my rise table. So this will be R, and then I, and then C, and then E. Okay, so remember R is the ratio, right? And then this is the ratio, and then this is initial what? Initial moles, and then this is the change, and then this is gonna be equilibrium mole. Equilibrium what? Moles, meaning the moles at equilibrium. However, guys, because we are dealing with moles, you're probably going to need equilibrium concentration also. Okay, you're gonna need an extra column for equilibrium concentration. So just keep that in mind. Now, the ratio now. Where are you? Yeah. So in terms of the ratio, we are dealing with A2. I'm gonna write it at the top here. A2, which is a gas. Guys, my columns they are not. I need to add another one. Unless it's not a train smash, we can still fix it. Okay, all fixed. So we have A2, which is a gas, and then we have 2B, which is also a gas, and then you have 2AB, which is also a gas. Now guys, if we can remember, we said the numbers in front are the ratios. So it means here we put 1, here there is 2, so you put 2, here there is 2, so you put 2. Those are your ratios. Before you even go further, remember on change that this 1, now you're gonna write it as plus 1x. Why do we write it as plus 1x? This because remember the ratios give you the change, but we are putting plus because it's a reactant. Same with this one, it's a reactant, so we put plus, and then we put this number, we say 2x, And then the product, we say minus, then we say 2x. Okay, because the oh my goodness, no let's just fix that. Remember, reactants are used up, so we put minus for them, and then minus 2x, and then plus 2x. Plus because the products are being formed, minus because the reactants are being used to form the products. Right. Now the initial moles, what do we have? Now we still have x. Now the problem is, now I'm gonna use too many x's here, so maybe to avoid that, let me use a different symbol here. Instead of using x, let me use maybe y. Let's use y maybe. So here we're gonna have minus 1y minus 2y, and then we're gonna have plus 2y, just to, so that we avoid having the same symbol, right? And then next, where do we go to? We then say, we're told that initially there was x moles of A2 and then 2 moles of gas B. So here we put 2, 0, which is the 2 moles for B, initially. Then how much do you have for the product initially? Anyone who still remembers? So we have 0 initially for the product, because the product has not been formed, right? We don't start, I usually say, we don't start with the pap. If we want to cook pap, we start with the ingredients first. So it's only the reactants that are there first, and then you start making pap. Now at equilibrium, what information do we have? We're told that it is found that 0.4 moles of gas AB is present. So here we put 0.4 moles, and then for AB, very important, that is for AB, 0.4 moles. And then we don't know how much of this one we had, we don't know how much of this one we had. Then we are immediately told that the Kc is that. Right. So this question, guys, is super easy. You know what you should just look for? The most important part, you just look for the ice part. The ice part that is filled. What am I saying? This part, as long as you have something about the initial and something about the equilibrium, you are okay. You can use that ice part to find out what is y, and then you are done with the question. You will be fine, and more fine. So you simply say 0 plus 2y is equals to 0.4, right? 0.40. So you put it like that, because remember I told you I plus C gives you E. I plus C gives you E. So now 2y is going to be equal to 0.4. If you divide by 2, that means your y will be 0.2. So therefore, guys, we should be happy since we got our y to be 0.2, because now here I know I'll just put 2 times 0.2, okay, which gives me 0.4, right? So now I know that here it's simply 0.4, which makes sense, because it means from 0 you added 0.4 to get what? To get 0.4. Then here I'm gonna remove the 2y now. Let me just write it properly. 0.4. Remember, our y is 0.2, so I'll say minus 2 times 0.2 gives me minus 0.4. Guys, that's why in whatever I wrote on change here, you write it in pencil. So you have minus 0.4. Same here, it's gonna be minus 0.2. Okay, then now that you have this, guys, you simply now say 2 minus 0.4 gives me what? 1.6. And then x minus that, I don't know how much will that give me, but I know it will be x minus 0.2 here. Then you're okay. Remember, these ones you are minusing, these ones you are adding. So 0 plus 0.4 gives you that. Then that is okay, guys. That is very good. So now you just have to find out the equilibrium concentration. Concentration, remember guys, we use C is equals to N over V. Okay, we use C is equals to N over V. Let me just fix my columns here and then have this line there. Alright, so let's also remove this. So now, how do you calculate concentration, guys? You simply say the number of moles over the volume. So the number of moles here is 0.4. Then you're going to divide by the volume. The volume you're given that it's a 1 decimeter cubed container. So you divide by 1. Here you also divide by 1. And then here you also divide by 1. Then guys, you are happy. You are fine. Why am I saying that? Because the equilibrium concentrations, what I didn't mention, I forgot to mention, is that in the KC, we are only putting the concentration of these things. Okay, we're only dealing with the concentration of those things. So that's why we needed this thing for equilibrium concentration. So now we then say KC is gonna be equal to, what is your product? Your product is AB, right? So you put AB. What is the ratio for AB? It's 2, so that becomes your exponent. And then which ones are your reactants? It's A2. It's A2. And then what is the exponent? Is 1. And then the other reactant is B. What is your exponent? It's 2. So therefore now, you were given Kc, guys. You were given that Kc is 0.5. So we simply put what? 0.5 here. What about AB? Well, the concentration of AB is this one, 0.4 over 1. It's gonna still give you 0.4. So you say squared. And guys, when you put here now, you put round brackets. But here you use square brackets because it's concentration. Ne? It's concentration. And then A2, the concentration of A2 is x minus 0.2 over 1. So it's x minus 0.2 over 1. And then the exponent is 1. What about for B? It's 1.6 over 1, which is simply 1.6. Then you say squared. Why is it squared? Because the ratio is 2. So guys, after that, you simply now find your what? Your x there. It's just simply solving for x. I usually say the last part is just maths. So you say 0.4 all squared. You multiply it by 0.5 times the x minus 0.2 times the 1.6 all squared. You are now doing maths, heavy maths. So you divide by 0.5. You also divide by 1.6 all squared. You divide by 0.5 and also 1.6 all squared. So this cancels that, this cancels that. Then you're going to have x minus 0.2 being 0.4 all squared divided by 0.5, 1.6 all squared. Now you can simply say, therefore, x will be, you take the 0.2 to the left, you will have 0.4 all squared divided by 0.5, 1.6 all squared plus 0.2. Then you then go to your calculator at once. So if you put it in your calculator there, so you get 0.33 moles. Now what does this mean? This means initially, right? Initially we started with 0.33 moles of A2. Okay, we started with 0.33 moles of A2 while we started with 2 moles of B. All right, so that is how you get that answer there. Sometimes they can even say calculate the initial mass. Getting initial mass means you get the number of moles first, then you just convert the moles to mass by using the formula N is equals to M over molar mass. So you substitute N, which is the number of moles you would have gotten. You get the molar mass of that thing. You check your periodic table. Then you can get the mass, the initial mass. Okay. So I hope this is clear, guys. Is there any question? Okay. Um, no problem. Don't you wanna try it actually? Okay, yes. Then I'll walk you through the solution, ne? Okay, perfect. It says that initially X moles of hydrogen gas are mixed with 0.3 moles of carbon dioxide, which means this one we know initially. Now we know the volume also. When equilibrium is reached at a certain temperature, it is found that 0.2 moles of H2O are present. So we are given the equilibrium information about H2O. So here I'm probably gonna need another another column here on my table for Kc. Then I will write here ratio, and then so it's rise. So this is equilibrium mole, and then this is equilibrium concentration. Now please do show them that concentration is N over V there. Now the ratio, we're working with H2 gas, we're also working with CO2 gas, and then we're working with H2O gas, and then CO gas. The ratio now, is this thing balanced? They said it's balanced already. So that's nice. We have 1 1 1 1. That's a nice one. Now for change, we're gonna use, since they said X moles, I'm gonna use Y again. So remember, reactants are being used up, so we say minus Y, meaning 1Y, get 1Y. And then here we say plus Y, and then plus Y, because the products are they're increasing, right? They're increasing, so we use plus. Now initially we have H2X, we have X of H2 and then 0.3 of the carbon dioxide. How much do we have initially for these ones here? This I was not supposed to write. For some reason I wrote plus here. So we're simply gonna say 0 because initially we don't have the products. Now we are told that at equilibrium there is 0.2 moles of water. So that means here we put 0.2. Then you should be happy because you have your ice thingy there. So 0 plus y give me 0.2, guys. This means that our y is 0.2. So therefore I start fixing there, and I have to now start writing 0.2 everywhere. So this one I write 0.2. I'm also gonna write 0.2 here, minus 0.2 here, minus 0.2. So we say minus 0.2 minus 0.2 and then plus 0.2 plus 0.2. Right, that's perfect. Now 0 plus 0.2 gives me 0.2. 0.3 minus 0.2 gives me 0.1. X minus that will be X minus that. Okay, then the concentration now, I have to say this row, I have to divide this row by the volume, which is 10, because these are my number of moles. I want to divide them by 10 so that I get the equilibrium concentrations, because those ones are the equilibrium moles, the moles we have at equilibrium. Now we want to know the concentration at equilibrium, so we use the equilibrium moles. We say 0.2 you divide by 10. You say 0.2 you divide by 10, 0.1 you divide by 10, x minus 0.2 you divide by 10. By the way, here the answer will be 0.01, here the answer will be 0.02, here the answer will be 0.02. Please write the answers. Write the answers. Now we have to get x. So now we can therefore say what we call Kc. We are given the Kc that the Kc was 4. So if Kc is 4, okay, we will talk about that. Now Kc is gonna be equal to, now the product is H2O and CO, so we say H2O, and the exponent is 1 because it's just 1 here, guys. 1 1 1, or you can check this row here. So H2O and then CO, and then H2 and then CO2. Right, Kc was given to be 4, and then H2O, guys, for H2O is 0,02. Remember to use round brackets. And then for CO it's also 0,02, and then for hydrogen it's x minus 0,2 divided by 10. And then for carbon dioxide it's 0,01. Then, guys, it's a matter of getting the answer now. Cross multiply 0,02, 0,02, and then 4 into x minus 0,2 over 10, and then 0,01. Then we're going to divide by 4 into 0,01, divide by 4 into 0,01. Then what are we going to have? This would cancel that, this would cancel that. So it means we're left with x minus 0,2 over 10, and then you have 0,02 divided by 4 into 0,01. Then when you multiply by 10 and multiply by 10, by the way, guys, all this process I'm doing of solving for x, it doesn't have any marks, ne? Just so that you know, it doesn't have any marks. And then 0,02 divided by 4 into 0,01, and then it will be equal to x minus 0,2. So therefore my x will be 10 into 0,02, 0,02, 4 into 0,01 plus 0,2. Then you put it in your calculator. They only mark the final answer. Everything else we're doing there is just playing, eh? So when you put it in a calculator, I believe we should get, so if you put it in a calculator, I believe you get 0,3 moles, and then that will be your answer there. Okay, that will be your answer. So it means here the answer is so here it means we have 0,3 moles. Now that we know the answer, it means here it was also 0,3 moles, which means that they started with the same number of moles of this and also of that. And then now another thing is that now if you put 0,3 here, and then you put, so it will be 0,3 minus 0,2, which is 0,1, so you'll have 0,01. So here now you put 0,01. Now if you can check, if you add 0,01 plus 0,01, you get 0,02. And then here if you add 0,02 plus 0,02, you get 0,04, which means the products are more than the reactants, which is why your Kc value was greater than 1. Okay, so guys, I hope that we understood this, right? I'm hoping that I didn't lose you anywhere. This is how we solve it. Any questions so far? Now, factors that affect equilibrium. Factors that affect equilibrium. Now, we have already reached equilibrium, right? And we have a certain concentration of the reactants and a certain concentration of the products, right? So one might decide to disturb the equilibrium. For example, let's say that I'm dealing with A, right? Maybe A2 gas, the very same thing we had. I think it was A2 and 2B. A2 and 2B. Or A2 and B, which is a gas, and then they form form what the AB. Then we put 2 here to balance, right? We put 2 there to balance. Now this is what we have. Okay, so now we can decide to disturb this equilibrium. How can we do that? We can disturb it by either changing one of these 3 factors. You can change either the concentration, you can either change the concentration of one of them, or you can change the pressure, right, of the whole system, or you can change the temperature of the whole system. If you're changing pressure, you're doing it to the whole system. If you're changing temperature, you're doing it to the whole system. But if you change concentration, you're only doing it on, you change it on one of the species. Maybe you change this concentration of this or that or that. Now a nice way to remember it is Cape Town. Cape Town are the factors that affect your equilibrium. Cape Town, CPT, concentration, pressure and temperature. Now what were to happen if we pump in more A2 gas? If we pump in more A2 gas, what is gonna happen? It means we will have increased the concentration of A2. Remember, Gary, when you reach equilibrium, the concentration of the reactants is no more decreasing and it's not increasing. Same as the concentration of the products, it's not increasing, it's not decreasing. Now if you come in and then now you decide to say, no, I'm gonna just add more A2 manually, you can pump it in. You can pump it in, maybe, and get these things will be happening in a container, maybe and it should happen in a sealed container. So maybe you can just put a hole there and then you start pumping in more of the A2. So if you do that, you are disturbing the equilibrium. Okay, you are disturbing the equilibrium. So we have a man who studied this and then he came up with a principle that help us to understand what is gonna be the reaction, or rather the response of the system, and that is called Le Chatelier's principle. Le Chatelier's principle. We must know how to state it. So it says when the equilibrium in a closed system is disturbed, the system is gonna reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. The system is going to reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So it's 2 things that are happening, or actually 3. The system is being disturbed. What does it do? It reinstates a new equilibrium by doing what? By favoring the reaction that will oppose the disturbance. Okay, so what this means is that if you pump in more A2, that means there will be now an increased amount of concentration for A2. The system is going to then reinstate a new equilibrium by doing what? It's going to favor the reaction that will oppose this disturbance. Now, what disturbance have we imposed on this reaction? Is that we have increased the concentration of A2, which is something that was not there, that was not happening initially. It's something that was not supposed to happen because the things had reached equilibrium. So now it's gonna oppose that by favoring a reaction that will use up more A2. Now, which reaction uses more A2? Is it the forward reaction or the reverse? Yes, it's the forward reaction, right? is the forward reaction, is the one that will use up A2. So that means if we pump in more A2, the first thing is that if they say use Le Chatelier's principle, you say according to Le Chatelier's principle, the system will reinstate a new equilibrium by favoring the forward reaction. So to favor the forward reaction, and by favoring the forward reaction, right, it then decreases the concentration of A2. It decreases the concentration of A2 gas. Okay, that is how the system is going to respond. What if we increased, let's see, what if we increased B2? What do you think the system is gonna do? Which reaction is gonna be favored? Can you please type for me forward or reverse there? Correct, the forward reaction, because that reaction will be using up, the forward reaction uses up B, so it's gonna favor the forward reaction. And then what if we increase AB? If we increase AB, what's gonna happen? And I always say that disturbing the equilibrium, it's like being naughty. Kore is a clear definition of being naughty, shame. You know, it's like a small child. Things are very much organized, and then the small child will just come and mess up everything. You know how kids are, they are so naughty. So even here, it's our way of practicing our mischievous deeds here on equilibrium. So here you are, the system has reached equilibrium. Then when you come in and say, what is gonna happen if I pump in more AB? You take AB from somewhere that was already produced, you come in and then you pump it into the reaction. Isn't that mischievousness? Is it called mischievousness? Yeah, but it's I hope you get what I'm saying. So now guys, by pumping in more AB, the system is gonna be like, you think you are clever, so you know what, we'll favor the reaction that is gonna reduce AB. And which reaction is that? It's going to be the reverse, right? It's gonna be the reverse, because the reverse uses up AB to form A and B, because it's actually decomposition. It is a reaction which splits AB into A2 and B. So that's how the system will respond. Now, what if instead of increasing, what if we start to take out some of the A2 that is there? Meaning, what if we're reducing the concentration of A2? If you reduce the concentration of A2, the system is going to be like, since you are reducing A2, I'm going to favor the reaction that is going to increase A2. Which reaction is that? Forward or reverse? So indeed, it's going to favor the reverse reaction. And therefore, a new equilibrium will be reached. A new equilibrium is going to be reached. What if we decrease AB? What if we take out some of the AB, we reduce it? What is it going to do? It's going to favor the reaction that will increase AB. Which reaction is that? It's the forward reaction. Guys, that's how simple it is. That's how simple it is. But nowadays, recently, these questions were easy like this, but nowadays they've made them more interesting. I'm gonna take this reaction here. So recently they like questions like this. They will tell you that it is noticed that the solution, right, in the solution, right, in the container becomes more brown after then they want you to explain according to Le Chatelier's principle, to say what change could have been done on the system. So if the solution becomes more brown, when I should understand that the color that the system is becoming means that the reaction that was favored is going to that color. If the solution becomes more brown, this means the forward reaction was favored. That is the first thing. It means the forward reaction. Wow, let me see if I can do this. Nice. The forward reaction was favored. That is the first thing. How do we know that the forward reaction was favored? This is because the solution became more brown. If it becomes more brown, it means you are forming more of this 2NO2 because that is the brown gas. So the forward reaction was favored. And if the forward reaction was favored, that tells you that, which means that N2O4 was being used up more, more. You understand? So that means this one was being used up more because now it's being used up to form the brown gas. Now if it was being used up more, what happened in the first place? Why would the system just decide to use up N2O4? Well, it's because more of it was added. More N2O4 was added, and that is how the system was disturbed. You understand? That is how you work backwards. So just understanding that, number one, if the solution becomes more brown, it means the forward reaction was favored. If the forward reaction was favored, that means N2O4 was being used up more to move from here to there. And if this was being used up, why would the system just decide to use up N2O4 more? The system, in isiZulu bare, angithi umuntu othi uyangisukela. So similarly, the system isn't just, your eye in Zulu is tough shame, but then it's fine. The system isn't just being mean or cruel to N2O4. The reason why N2O4 is being used up more is because more of it was added by someone. You understand? That's how you trace back the steps. Similarly, I'm just going to give you, let's say that you have A plus B, right, reacting to form C plus D. Or better yet, let's use this one, that Na plus ions, right, plus Cl minus ions. No. This is how they like to do it. They say sodium plus chlorine gas, right, they react to form, this is not the reaction I wanted. The one I want is ions, and you know where we can get it? We can only get it in our table 4b, but then it's fine. Let's say this forms sodium chloride, and then maybe it will be 2 here and 2. Let's say this is pink for just example, and then brown, and then yellow. And then they say that a student, right, after disturbing the equilibrium, maybe it was found that, or after adding something, it was found that the system became more brown. Then they say explain, what actually happened. So if the system becomes more brown, which reaction was favored? It means the reverse reaction was favored. The reverse reaction was favored. Now, if the reverse reaction was favored, that means what was being used up more, because now if you're going to the left, means you are using something where you are coming from. That means you are using NaCl was being used up more, which tells you that perhaps NaCl was added. So when you write this question, right, you write it backwards. This is your first statement, second statement, and this is your last statement. When they say explain why the solution becomes more brown, explain why the solution becomes more brown, you tell them that sodium chloride was added. It being added means it was now being used up more. That means the system favored the reverse reaction. You understand? So when you write it backwards, but the understanding is, is from that. Okay guys, now it's not only concentration that affects the equilibrium. Sometimes you can do pressure, and you can increase or decrease pressure. Now when you increase pressure, if you increase pressure, you favor the reaction with less moles, less number of moles. And then if you decrease pressure, you favor the reaction with more number of moles. So indeed, if you increased pressure here on this reaction, you're gonna favor the reaction that produces less number of moles. And if you can check here, Ankere here it's 1, we have to count it as 1. So the number of moles on the left is 3 moles. It's 3 moles. While the number of moles on the right is 2 moles. Right. So if you increase pressure, then you're gonna favor the forward reaction because it produces less moles. But if you decrease pressure, you're gonna favor the reverse reaction, which produces more number of moles. That's just how we need to remember it. Now, this pressure thinking, right? They don't only like to ask about it directly like that. They can give you something like this, and you know what they say? They say to you, they say volume was decreased. They say volume was decreased. So tell us, or which, according to Chatelier's principle, which the solution is gonna have maybe which color, right? Which color are we gonna have? If volume was decreased. So once they talk about volume, I taught you about pressure. So you have to know that according to there's this formula for Boyle's law. It says pressure is inversely proportional to volume. Boyle's law, we did it in grade 11. So what happens is that volume and pressure are vice versa. If you increase volume, it means you decreased pressure. You see? So now you must take it as to say, so it means pressure was decreased. No, pressure was increased because volume was decreased. And volume was decreased, so it means pressure is going to increase. And since pressure was increased, this favors the reaction with less number of moles, meaning it favors the forward reaction. That is according to Chatelier's principle, right? Turning the solution into pink. Turning the solution into more pink or pinkish. That is what we have. Okay. So that is how we deal with volume. It's just vice versa of pressure. And then lastly, the other factor is temperature. Now, how does temperature affect the rate of a reaction? This one, it necessitates you to understand the difference between endothermic and exothermic reaction. Now let's understand that this symbol here is for endothermic reaction, and then this symbol here, which is negative, saying enthalpy is negative, is for exothermic reaction. I usually just remember this by remembering that your X is someone who's not really positive into your life, right? So yeah, now what you must understand about endo is that endothermic reaction releases energy. It releases what? Energy. While exo, no, I'm lying. Endothermic, it absorbs energy. It absorbs energy. While exo, it releases energy. Just like how you release you release someone from your life and they become your ex. So exo releases energy. Releases energy. Okay? Now, since exothermic reaction releases energy, the container will start to feel warm. Then, since endo absorbs energy, the container will start to feel cold where the reaction is occurring here. Okay? So if you increase if this reaction is an endo, when you touch it here, when you touch the container, it will be cold. So endo, it will be cold because it absorbs energy and keeps it inside on the core, in the bonds. While exothermic is releasing energy, so when you touch the container, it's gonna be hot or warm. Just like how your ex become very good looking after you break up. You know, guys, this is just something you can use to remind yourself. Now, so X hot, ne, endo cold. Now, if you increase temperature, you must first check whether the reaction is it endo or exo. So here I'm gonna give you that this reaction here is exothermic. This reaction is exothermic. Now, when you must start here and understand that since the reaction is exothermic, it's already hot. Ne? So since it's already hot, if you increase temperature, you're gonna favor the reaction that decreases that hotness. You see, that decreases that high temperature. And which reaction is that? It's gonna be the endothermic reaction. Now, another thing to understand. So when you increase temperature, you favor the endothermic reaction. But if you decrease temperature, then you favor the exothermic reaction. That's how it works. You favor the exothermic. So remember that if you increase temperature, you can't favor the exo, because you are going to make the container to be more hot. The system says that since the system will look at whether the reaction we're dealing with is it endo or exo, and then it's gonna decide which one to choose. Now, what I want to caution you on is that this enthalpy here, and it's saying less than 0, it's saying exo. That exo is for the forward reaction. Please know that it's for the forward reaction. And since it's the forward reaction, that means endo will be the reverse reaction. Quite important to note. That means reverse reaction is endo, the forward reaction is exo. Exo and then endo. This one that is here talks about the forward reaction. It's talking about the forward reaction. right? So for example, let's say I have the following. Now let's give this one a try. This endo, right, means the forward reaction is endo, because this is less than 0. Oh, it's exo because it's less than 0, it's negative. So this is exothermic reaction, and that exo is for the forward reaction. So it means the endo is for the reverse. This is always the first thing you need to identify. Now if you increase temperature, the system will want to decrease the temperature, so it's gonna favor the reaction that brings down the temperature, which is the endothermic reaction. It favors the endothermic reaction. Then since the forward is exothermic, therefore it means the reverse is the one that will be favored. That is it. And then what about if we decrease temperature? If you decrease temperature, you're gonna favor the exothermic reaction. Favor the exothermic reaction. Now since we are favoring the exothermic reaction, therefore the forward reaction will be favored. Why? Because we said the forward reaction is the one that is exothermic. Right. So good people, I hope you understand how these factors affect equilibrium. Okay. I hope that you understand how they affect equilibrium. So the last chapter after this is the graphs, whereby we have to talk about the graphs and look at these changes graphically, or when the increase in temperature and the likes. We need to look at it graphically, which we'll do that on our next lesson. For now, you can just try to do questions, previous papers, especially on calculations, but preferably that don't require graphs, because I know most of the times they like those graphs. So yeah, any questions so far?